Dear students, in this session we are going to study the circuit diagram for the transistor as a common emitter amplifier. We see the circuit diagram here and the configuration of the transistor NPN transistor in a common emitter mode is shown here. We see the emitter is grounded, a very small base current is shown here. And what is the input? The input is the difference between VBB and a very small alternating input signal which is called as a Vi. So the difference between these two is fed as the input to the transistor. We see the collector current, we see the load resistance and the amplified output voltage. VO is equal to beta times delta IB into RL. Now this equation, beta is the current gain. So if we remember the output characteristics of the transistor, look here that for every step of say 10 microamperes of the base current, we see a sharp rise of 2 milliamperes of the output current. That means if we say that if the input is somewhere changing around 10 microamperes, the output is changing to 2 milliamperes, that is almost 200 times, and this 200 is nothing but the current gain beta. So here the output is equal to beta. Suppose it is 200 multiplied by delta IB. So here is the factor that always gives rise to the magnified or say amplified output here. Look at this equation. In this equation we know that beta somewhere is around 200 into delta IB, whatever it may be, multiplied by RL. So however small variation will be, it is amplified how many times? It is amplified almost 200 times. It depends on this value. It may amplify 200 times or it may get amplified 2000 times, and this property of the amplification is used for the common emitter amplifier, and the transistor acts as an efficient device to amplify the voltage signals. So this is used in loudspeakers and public address systems where a signal of very less strength is amplified, say more than 10,000 times for a large audience capacity. So the next is we are going to study what is an oscillator. An oscillator is a device with infinite gain. What is gain? Gain is the ratio of the output to the input. Gain, or say A, it is called as VO upon VI. Now in this oscillator we see that a small part of the output is fed here, and this feedback network is given as the input again. So this process goes on continuing till a certain factor where the input requirement becomes 0. So it is only output divided by 0 input, and we get a amplifier or whatever it is with an infinite gain. So that is how the denominator becomes 0. Ultimately the value becomes equal to infinity. So this is the principle of an oscillator. Now there are two types of feedbacks. When the input is in phase with the main signal, we call it as a positive feedback, and when the input has a phase difference of 180 degrees, it has a negative feedback. Also we have Barkhausen criterion, where the gain with feedback should be greater than or equal to 1. The last point in this chapter is about logic gates, and we start here with the first gate, which is called as the input, which is called as the AND gate. Now in case where are gates used? Gates are used in different electronic devices where they recognize the signal as high or low only. Low means 0 and high means 1. So it is an electronic circuit which has 2 or more inputs and 1 output. It produces high output when all of its input are high, and they or else the output is low. So this is the block diagram of a AND gate. How to remember AND? This D of AND represents the AND gate. We have the input as A and B and the output Y is equal to A and B. So A dot B here is the output. So if A is 0, B is 0, the output is 0. If A is low, B is high, then also output is low. If A is 1, that is high, and B is low, the output is naturally 0. But only when both A and B are high, we get a output high. So the AND gate works only when the both inputs are high. So that is called as the truth table for the AND gate. The second easier gate is called as the OR gate. See, the OR gate functions when any of the inputs are high, it does give a high output. So this is the diagram of the OR gate, and we have the truth table. Say when A is 0 and B is 0, the output is 0. When A is 0 and B is 1, the output is 1. When A is 1, B is 0, output is 1. When A and B both are high, the output is 1. Now this is an inverter gate, and it is called as a NOT gate. Whatever input is fed to becomes inverted and gives an opposite output. Suppose the input is it has only one input and one single output here. So if the input is 0, output is 1 high. If the input is high, output is low. Now we can combine this NOT gate to other gates also. That is, if the NOT gate is combined with the AND gate, we get here a NAND gate. We see. So this is the AND gate, this is the NOT gate, and the combination gives rise to a NAND gate. So whatever truth table of the AND gate is there, it is opposite here. So for the AND gate we have 0, 0, 0, 1. But for the NAND gate we have the reverse of the table. That is, these conditions are same, but here it is 1, 1, 1 and 0. Okay. We study the last gate here, and this is called as the NOR gate. It is a combination of the OR gate and the NAND gate, and exactly we see that instead of 0, 0, 0, 1, we have 1, 0, 0, 0. So that those are the 5 basic gates, and here we are about to end our chapter on